Friends, welcome to the class. Today we'll discuss about Euclid's division lemma. Euclid's division lemma states that for any two positive integers, say a and b, there exist two unique integers, say q and r, such that a equals to bq plus r, where 0 less than equals to r less than b. That means, in other words, we can write it as dividend equal to divisor into quotient plus remainder. For example, 16 equals to 5 into 3 plus 1. Here dividend is 16, divisor is 5, quotient is 3, remainder is 1. Let's see an example. So that the square of any positive odd integer is of the form 4m plus 1 for some integer m. Let a be any positive odd integer. Then on dividing a by b, we have a equals to bq plus r, where 0 less than equals to r less than 2. This implies r can be either equals to 0 or 1. If r equals to 0, then a equals to 2q, which is divisible by 2, so 2q is even. If r equals to 1, a equals to 2q plus 1, which is not divisible by 2, so 2q plus 1 is an odd. Since a is odd and it cannot be of the form 2q, so a is of the form 2q plus 1. Thus, any positive odd integer is of the form 2q plus 1. Now, a square equal to 2q plus 1 whole square, or a square equal to 4q square plus 4q plus 1, because x plus y whole square is x square plus 2xy plus y square, or we can write it as a square equals to 4 into q square plus q plus 1, or it is a square equal to 4m plus 1, where m equal to q square plus q. Thus, for some positive integer m, the square of the integer is of the form 4m plus 1. Hence proved. So that the square of any positive integer is of the form 8m plus 1, where m is some whole number. Let a be any positive odd integer. So a is of the form 2q plus 1, where q is a whole number. That means a equals to 2q plus 1. Now a square equal to 2q plus 1 whole square, or it is equals to 4q square plus 4q plus 1, or we can write it as 4q taking common 4q into q plus 1 plus 1. Let this is first equation. Now q into q plus 1 is either 0 or even for any whole number q. Let q into q plus 1 equals to 2m, where m is a whole number. So equation 1 can be written as 4 into 2m plus 1, or equals to 8, or this implies a square equals to 8m plus 1. Thus, for any positive odd integer, the square is of the form 8m plus 1. Hence proved. So that the cube of any positive integer is of the form 4m, or 4m plus 1, or 4m plus 2 for some integer m. Let a be any positive integer. Then by Euclid's division lemma, the corresponding to the positive integer a and 4, there exist non-integers q and r, such that a equals to 4q plus r, where 0 less than equals to r less than 4. Now a cube equal to 4q plus r whole cube, or on expanding it is equals to 64 q cube plus 48q square r plus 12qr square plus r cube, because the expansion of x plus y whole cube is x cube plus 3x square y plus 3xy square plus y cube. Let this is first equation. Now the possible values of r are 0 or 1 or 2 or 3, because here 0 less than equals to r less than 4, so r cannot be more than 4 or equal to 4. So therefore the values of r are 0, 1, 2 or 3. Now if r equals to 0, putting the value of r equals to 0 in equation number 1, we get a cube equal to 64 q cube, or it can be written as 4 into 16 q cube, or a cube equals to 4m, where m equals to 16 q cube. It is an integer. When r equals to 1, we get a cube equals to 64 q cube plus 48 q square plus 12 q plus 1, or it can be written as, taking 4 as common, 4 into 16 q cube plus 12 q square plus 3q bracket ends plus 1. So it is of the form 4m plus 1, where m equals to 16 q cube plus 12 q square plus 3q, which is an integer. When r equals to 2, we get a cube equal to 64 q cube plus 96 q square plus 48 q plus 8, or taking 4 common, we get 4 into 16 q cube plus 24 q square plus 12 q plus 2, or it is of the form 4m, where m equals to 16 q cube plus 24 q square plus 12 q plus 2, which is an integer. Now, when r equals to 3, we get a cube equals to 64 q cube plus 144 q square plus 108 q plus 27, or we can write it as 64 q cube plus 144 q square plus 108 q plus 24 plus 3. Here we're breaking 27 in the form of 24 plus 3. Or taking 4 common, we get 4 into 16 q cube plus 36 q square plus 27 q plus 6 plus 3, or which is of the form 4m plus 3, where m equals to 16 q cube plus 36 q square plus 27 q plus 6, which is an integer. Hence, the cube of any positive integer is of the form 4m or 4m plus 1 or 4m plus 3 for some integer m. Hence proved. Let's discuss about Euclid's division algorithm. Euclid's division algorithm is a technique to compute highest common factor, or HCF, of 2 or 3 given positive integers. According to this, the HCF of any two positive integers with a and b, where a greater than b, is obtained as follows. Step 1. Apply the division lemma to find q and r such that a equals to bq plus r, where 0 less than equals to r less than b. Step 2. If r equals to 0, then HCF is b. Step 3. If r not equals to 0, then we need to apply Euclid's division lemma again to b and r. We need to continue the process till the remainder is 0. The last divisor is a HCF of a and b. Let's see some examples so that we can understand it easily. Use Euclid's division algorithm to find HCF of 176 and 38,220. The given numbers are 176, 176 and 38,220. Here 38,220 is greater than 176. So by following Euclid's division lemma, we get 38,220 equals to 176 into 217 plus 28. Here the remainder is 28, which is not equals to 0, and b equals to 176. So again, taking 176 as dividend and 28 as divisor, applying Euclid's division lemma, we get 176 is 28 into 6 plus 8. Again, the remainder is 8 and it is not equals to 0. So again, applying Euclid's division lemma, we get 28 equals to 8 into 3 plus 4. Again, the remainder is 4 and it is not equals to 0. So again, applying Euclid's division lemma, we get 8 equals to 4 into 2 plus 0. Here the remainder is 0. So the last divisor is 4. Hence, the HCF of 176 and 38,220 is 4. This is the answer. Using Euclid's division lemma, find the HCF of 180, 252 and 324. The given numbers are 180, 252 and 324. And here 324 greater than 252 greater than 180. So taking 2 at a time, applying Euclid's division lemma for 324 and 252, we get 324 equals to 252 into 1 plus 72. Here the remainder is 72 and it is not equals to 0. So again taking 252 as divisor and 272 as divisor and applying Euclid's division lemma, we get 252 equals to 72 into 3 plus 36. Again the remainder is 36 and it is not equals to 0. So again applying Euclid's division lemma for 72 and 36, we get 72 equals to 36 into 2 plus 0. So here we got the remainder 0 and the last dividend is 36. The last divisor is 36. Thus the SCF of 324 and 252 is 36. Now applying Euclid's division lemma for 180 and 36, we get 180 equal to 36 into 5 plus 0. Since remainder is 0, SCF of 180 and 36 is 36. Hence, the SCF of 324, 252 and 180 is 36. Let's see an word problem. Two tanker contains 850 liter and 680 liter of petrol respectively. Find the maximum capacity of a tanker which can measure petrol of either tanker in exact number of times. Given capacities of the tanker are 850 liter and 680 liter. Here 850 is greater than 680. So following Euclid's division lemma, we have 850 equals to 680 plus 170. Here the remainder is 170 and it is not equals to 0. So again, following Euclid's division lemma for 680 and 170, we have 680 equals to 170 into 4 plus 0. Here the remainder is 0 and last divisor is 170. So we can say that the SCF of 850 and 680 is 170. That means the maximum capacity required container is 170 liter is the answer. Friends, here we saw few examples, few questions. The more and more such questions you practice, the easier it becomes and the more you like it. So friends, practice more and more such questions. And in case you come across any difficult question, feel free to share your questions with me. It will be a pleasure for me if I can help you out in solving your doubts, in solving your questions. So this much for today's class. Thank you.